So we've now looked at the thickness of that boundary layer. We've gotten, it's an interesting engineering result that the boundary layer is very thin. We can estimate the size of that boundary layer, calculate it pretty accurately, actually, if we want to. But that's not really an engineering result. So let's try to get a real engineering result, which would be, for instance, estimating drag. So now the question is, okay, how much do we have to, push this plane? How hard do we have to push this plane to keep it moving through the air? So we're going to go ahead and try to estimate drag on the surface. So in order to do that, again, we just got some kind of no-slip surface here. Think of it as a plate or a wing or a wall, whatever you fancy. There's a flow traveling over the top of it, just as we've been doing. Same exact problem we've been looking at. But now we're going to try to estimate that drag. In order to estimate the drag, we're going to estimate the shear stress. So tau here is equal to mu du dy. So we know that's true. But now what we can do is try to estimate that with mu and the change in u and that delta, because that delta is the distance from which over which u changes from 0 at the no-slip condition surface to u infinity. Because beyond the delta, beyond the effects of viscosity, the flow is just traveling along at this u infinity. As I've said before, it doesn't even know there's a wall there at this point. It's just flying along at u infinity, has no idea there's a wall there. Whereas in the viscous boundary layer, it's feeling the effect of that wall. So we can estimate that du dy because that's the distance over which this u changes from 0 to u infinity. So we're going to go ahead and try to then figure out how to turn that into an actual estimate of drag force. So in order to do that, let's create a situation here. We'll give it some dimensions. So we'll try to estimate the drag force on a plate that is, we'll change the length just for fun. We'll make it 0.7 meters long. And we'll make it 3 meters wide. So 3 meters wide, that's the direction in and out of the paper. So nothing much is happening in that direction. That just gives us a proper three-dimensional object. And let's say it's traveling at u infinity equals 1.2 meters per second. Traveling through air at u infinity equals 1.2 meters per second. And I guess I haven't said this explicitly, though I'm hoping you all as engineers know this. It doesn't matter whether the air is moving 1.2 centimeters and the plate's just sitting there, or the plate's moving 1.2 meters per second through still air. That's the same problem. That's just a different, you just change reference frame. So actually there's no even way to know which is happening mathematically. So that's what's going on. So we've got a wing. It's got some some depth here. Sorry, it's got a width of 3 meters. You think of it as a blade or whatever. And then it goes back like this, 0.7 meters. And the flow is traveling over it across the surface from this direction. U infinity, or it's traveling through that surface. And it's going to have flow on both sides of the wing. So you're going to have delta up here. Now it's going to have delta down there. Now it's going to be the same top and bottom. The deltas are going to be identical on the top and the bottom of that wing, but nonetheless, we will have both. So we're going to have, x, and we defined this as y, and we defined this as x, and by the right-hand rule, that means then this will be z. So z will point that way. So there's your x, your y, and your z coordinates. Okay, right-hand rule, x, y gives me the thumb pointing that way. So there's my blade traveling through that, and I'm going to try to now estimate the total drag on that wing. All right, so this would be easy if I knew the average shear stress. So the force on the wing, or the total drag, would be the average shear stress times the total surface area, where this would be average shear stress. But I don't know that. I know that the shear stress is a function of x. So the shear stress is definitely a function of x. Because if you look at this delta, it's getting bigger, right? So as delta gets bigger, that shear stress is going to get smaller because we have delta u over that dimension. So it's going to be mu tau is of order mu times delta u over delta. So as delta gets bigger, the shear stress is going to get smaller. And we know that delta is a function of x. Delta u is not. That goes from u infinity to 0 over the whole flow. Mu is not. But delta is definitely a function of x. So we don't know t bar. What we know is t of x. So how are we going to do that? Well, you know how we're going to do that. We're going to integrate it, right? So that's what we're going to do. But let's set it all up, and then we'll see if we can integrate it. So we know that tau is equal to mu du dy, as we said. And that is definitely a function of x. So it depends on x. So tau is of order mu delta u over delta. So that's, notice I've changed from equals. This is the true definition of the shear stress. When I replace this du dy with delta u over delta, that's not the derivative. It's an approximation of the derivative. So I can go to the order sign here. I can go to an approximate symbol, but I need to recognize that I've switched from truly being equal to being an approximation here. And I know that delta is actually a function of x, which is why tau is a function of x. So I know the form of that because it's delta over x is equal to 4.92 times the Reynolds number based on x to the negative 1/2. So I can write delta of x here is equal to 4.92 times nu over u infinity x all to the 1/2. That's the Reynolds number based on x to the negative 1/2. I flipped it upside down times x because I brought this x over from the left to the right. So that looks like that. So if you want to put, obviously I'm not going to leave x here and x here. I'm going to multiply that x in. So I'm going to have delta of x is equal to 4.92 times nu over u infinity raised to the 1/2 power times x to the 1/2 power. So this is an explicit representation of how delta changes with x. So you know we're going to need to integrate this, right? We're going to need to integrate this across this surface in 2 dimensions, but it doesn't change in the z direction, right? It only depends on x. It does not depend on z. So d is d of x. D is not a function of z. So we don't need to worry about the z direction. It's going to be constant in this direction, but it is going to be not constant in this direction. So now you're going to try to use this delta of x to put it into this formula, and then use that to try to get your total shear stress. So you go ahead and try to solve that, and I will show you the solution in the next lecture.